Hello dear students. In this video, I'm going to discuss the solution to question number 20 using a shortcut method. So let us focus. We have a rectangular plane surface submerged in water. So we have the free surface and we have a rectangular plate immersed in such a way that its top is 1.5 meters below the free surface and its bottom is 6 meters. That means the height of the plate is 4.5 meters. All right, so we have to find the position of center of pressure below the free surface. All right, so let us take a look at the shortcut method to solve this question. So we have to remember that whenever we encounter any surface immersed in a liquid, all right, say this is a side view of any surface immersed in water or any other liquid, then first of all we need to draw a pressure diagram of this plate on this plate. All right, so let us say this is a rectangular plate or a square plate immersed in water. So the depth at this point may be h and the depth at this point may be h2. We have pressure at this point on the plate, or the pressure at this depth equals rho g h. All right, then let us say that the pressure at this point is rho g, the depth is h2, therefore the pressure is rho g h2. All right, so in between all the points below the free surface, that is between h1 and h2, the variation of the pressure is linear. So as we go on below the free surface, the pressure increases linearly, the static pressure increases linearly. So the pressure diagram looks something like this. All right, this pressure diagram is in 2 dimensions. All right, so this pressure diagram would look something like this in 3 dimensions. Suppose we are not able to concentrate on the width of this plate in this plane. All right, so let us picturize this plate immersed in water in 3 dimensions. So this is a plate in 3 dimensions immersed underwater. All right, so the pressure diagram would look something like this. All right, so this is the rho gh, that is this pressure. This would be again rho gh. All right, and at all points at this depth, that is the depth h, the pressure would be rho gh. All right, similarly at all points along the width, all right, which goes perpendicular to the plane of this paper. All right, so at all points at this depth, that is the depth h2, the pressure is rho g h2, because at a given depth the pressure is same at all points. All right, so let us draw a 3-dimensional pressure diagram on this plate, on this rectangular plate. Right, so this is how it looks. And what we have drawn here is just this one plane. All right, so we have the force acting on this plate all along its width, and that pressure diagram in 3 dimensions looks something like this. All right, so this is a pressure diagram on this rectangular plate. All right, so what this shortcut method says, all right, so we can use this as a shortcut method to find the force on a plate immersed in water, or force at any surface immersed in water, and the location of its center of pressure. All right, so we have to remember that the force on the surface immersed in a liquid equals the volume of the pressure diagram, or what we call as a pressure prism. All right, so we have to remember this whenever we have to solve for the location of the center of pressure or the pressure on a surface immersed in water. So the force on a surface immersed in water is equal to the volume of this pressure prism. So you take the surface, you draw a pressure diagram on this surface, and if the pressure diagram is simple, what you need to do is to simply find out the volume of this pressure prism, and that would give you the force on the surface. All right, so in this case the place is rectangular, so the volume of this trapezoid is easy to find. Similarly, if we have a square plate, we can find the volume of the pressure prism in a similar manner. Suppose the surface which is immersed in water, or the plate which is immersed in water, is not a simple geometrical surface. Say it's a triangle, so we have a triangular surface immersed in the water. So in the case of a triangle immersed in the water, it looks a little complicated to find the diagram of the pressure prism. All right, so the pressure prism would look something something like this. It would go on linearly increasing along the depth. All right, and it gets complicated as you draw. All right, so it's not a simple pressure diagram. All right, or a prism, or a three-dimensional figure of which you can find the volume easily by memorizing the formulas. All right, so in this case, in this question, the surface in question is the rectangle, and we have just learned that on a rectangle the pressure prism is in the form of a trapezoid. All right, so let us say whenever we have a trapezium, let us say this is a trapezium. All right, so in a trapezium we have two parallel sides and two non-parallel sides. Suppose the shorter side is A and the longer side is B, and this distance between the parallel faces is, say, L. Okay, so what we need to do is, if we have to find the location of the centroid, all right, the location of the centroid on a trapezium equals 2 times the longer side plus the shorter side upon the sum of shorter and longer side times 1/3 of this distance between the parallel sides. All right, so this is the location of the centroid from the shorter side. Let us say this distance is C. So C equals 2 times B plus A upon B plus A times L by 3. So we have to remember this formula for finding the location of the centroid of a trapezium. All right, so let's get back to the shortcut. So we need to remember two things. The force on a surface immersed in water is equal to the volume of the pressure prism. force on the surface equals the volume of the pressure prism. All right, and the location of the center of pressure is the location of the CG of this prism. All right, let me just read it out once again. We have two things: force equals volume of the pressure diagram or the pressure prism, and the location of force, location of pressure force, or the location of the center of pressure is at the CG of the pressure diagram or the CG of the pressure prism. Suppose the pressure diagram is, say, in the form of a trapezium or in the form of a trapezoid. All right. So force equals the volume of the trapezoid, and the location of the center of pressure is at the CG of this pressure diagram. All right, since the width is constant, we can say that the location of the CG of this trapezoid is at the CG of the pressure diagram in this plane. All right, because the width is constant, so the CG or CG of the pressure diagram, which implies the location of center of pressure, it can be simply found out by taking the CG of this pressure diagram. All right, so keeping this in mind, that the location of the pressure force is at the CG of the pressure diagram, we can use this to find the solution of this equation. All right, so this is the plate, and let me just draw it once again. So we have a free surface and a plate immersed at 1.5 meters and bottom edge at 6 meters. So the depth of the plate or the height of the plate is 4.5 meters. Let us draw the pressure diagram. The pressure diagram would look something like this. At this point, the pressure is rho g 1.5 meters because the depth is 1.5 meters. At this point, the depth is 6 meters. So the pressure at this point is rho g 6 meters. That is rho g h1 and rho g h2. All right, and at all points in between, the pressure variation would be linear. All right, now we have to find the location of the center of pressure. Let us say this is the line of action of the center of pressure. All right. Oh, okay. So the location of center of pressure, since this is a trapezium, the location of the center of pressure is at the CG of this trapezium. And we have learned that the CG of a trapezium can be found out using this formula. So if this is C, then C equals 2 times the longer edge, that is 6 rho g, plus the shorter edge, which is 1.5 rho g, upon the longer edge plus the shorter edge, times 1/3 of the depth of the plate, which is 4.5 meters. That is 4.5 upon 3. All right. So if we solve this, then the location of the CG of this trapezium or this trapezium pressure diagram in the shape of a trapezium is C equal to 12 rho g plus 1.5 rho g upon 7.5 rho g times 4.5 upon 3. All right, so C equals 13.5 rho g upon 7.5 rho g times 1.5. So if I solve this on a calculator, then it turns out that C equals 2.7 meters. All right, this multiplication and division is 2.7 meters. All right, so this depth is 2.7 meters. All right, so we have used the concept that the location of the center of pressure, right, this is the center of pressure, right? So we have used the concept that the location of a center of pressure is at the depth of the CG of the pressure diagram. So we had a pressure diagram in the shape of a trapezium, and the location of the CG of the trapezium from the shorter edge is 2b plus a upon b plus a times 4.5 by 3, so that turns out to be equal to 2.7 meters. So at a depth of 2.7 meters from the shorter edge, we have the CG of this pressure diagram. All right, so but we need to find out the depth of the location of the center of pressure. So the center of pressure, which is at the CG of the pressure diagram, is at a depth of 1.5 meters plus the 2.7 meters from the free surface. So this is 4.2 meters. All right, therefore the center of pressure, or the location of center of pressure from the free surface, is 4.2 meters. All right, so to conclude, we have to remember this equation. All right, and this equation is useful in cases where we have a plate with a constant depth, a constant width. All right, so whenever we have a plate with a constant width and we have to find out the location of the center of pressure, we should quickly remember that the location of the center of pressure on a rectangular or a square plate is at the location of the CG of pressure diagram. So the moment you see the center of pressure and a rectangular or a square plate, just quickly draw out the pressure diagram and then find out the CG of the pressure diagram. All right, so this formula is going to come out handy where the depth of the plate is constant. In case we don't have the plate of a constant depth, say we have a circular plate, and let us try to visualize how complicated the pressure diagram and the volume of the consequent pressure diagram on the circular plate would be. All right, so let us say that we have a circular plate immersed below the water, say at a depth h. All right, so the pressure at this depth will be rho g h. All right, so as we now move along the circumference of this plate, or at any point on the body of this circular plate, the pressure variation would have to be increased linearly as we move below the free surface. All right, so the pressure is increasing as we go down deeper and deeper. All right, so to, let us say, visualize the pressure diagram would look something like this. and you can like have a small idea how complicated this pressure diagram would be. It could look something like this, and all along this boundaries are circles. All right, so it's a little complicated to find out the volume of this type of a pressure diagram and then the consequent CG of this volume. All right, so just remember that whenever we have a square plate or a rectangular plate, we are going to use this concept that the location of the pressure force is at the CG of the pressure diagram. Although it's applicable to any surface, any plate, any pressure diagram, but it's feasible to use in the cases where the width of the plate is constant. All right, so we have a plate of constant width, then we can go ahead with using this formula. In these kind of cases, we can use the normal formula, which is yc equal to y bar plus icg upon ay bar to find out the depth of the center of pressure. All right, so the right option to this question is option C, which we have already found out earlier in the previous video, but in this video we have discussed how we can use a shortcut method to find out the location of the center of pressure. If you have any comments, if you have any doubts, feel free to reach out to me in the comment section and I'll be more than happy to answer your queries. Thank you for watching.